Swayam Prabha. Digital India. Educated India.
Hi and hello everyone. What we have been seeing was this queuing systems or queuing models with vacations. Okay. We have just introduced certain what is a vacation queuing model, and we have seen the MM1 vacation model with multiple vacations and how we can modify with the single vacation to single vacation model, right. What we will see next is the little bit more generic one, which is basically MG1 queues with vacation, right. The reason is we are not looking at in much generality GG1 because then the decomposition is what we want to see exactly. We did not see it in MM1 because we are going to see it in here, like in the case of MG1, because with Poisson input the decomposition holds both for queue length as well as waiting time. In the general GG1 model, it holds only for waiting time. That is what is the idea that you need to keep in mind. So, since we are taking MG1, which is a Poisson input model, so the queue length distribution level itself you will find the decomposition. Okay. So, we will now discuss this MG1 model with single and multiple vacations under exhaustive service discipline. Now, as usual, we will assume that the vacation sequence Vn is stationary and the system is in steady state. Now, let us introduce a random variable n star be the number of customers present at the start of a busy period, meaning the normal period following a vacation or vacation period, a vacation or a vacation period, because if it goes for multiple vacation and it will be after multiple vacation period. So, whenever the busy period starts, that means when the system becomes empty, the server will go for vacation. Now, after returning for vacation, either he will start serving the customer if there is at least one customer, or he will wait in case of single vacation period. Multiple vacation period, he will go for another vacation, right. So, whenever he starts the service, right, what is the number of customers present at the start of that busy period is what we call it as n star. So, clearly n star has to be at least 1, mean n star is greater than or equal to 1, and n star can be deterministic or a random variable, both is possible. Now, first consider this n star is a random variable which has a probability generating function which we call it as R of z, which is basically this quantity, which is the PGF of n star is what we call it as R of z. Let P of z be the PGF of the number in the system at a departure epoch of a usual MG1 queue without vacation. It is a normal MG1 queue without vacation is what the PGF of the departure epoch, but we know in such a queue the distribution of the number in the system at the random epoch or at the arrival epoch or at the departure epochs, they are all one and the same because of the Poisson input queue. So, and this P of z is given by the PK transform formula or Polak-Jekichin transform formula, right. We know all those things, right. That is what we take it from MG1 case. So, this P of z is basically the number in the system at the departure epoch. Now, Q of z is the PGF of the number in the system at a departure epoch of a MG1 queue with vacation. Okay. P of z is without vacation, Q of z is with vacation, and V of Z is another one which is PGF of the number in the system at a random point in time when the server is on vacation. This is at the random point, but when the server is on vacation. So, that number whatever be its distribution, and this V of Z is its PGF. Now, for Poisson input Q, the basic decomposition result is this. What is that? This is in a way Q length distribution with the departure epoch is given by this product of these two generating function. So, if you think in terms of a random variable, it is the sum of two independent random variables. One is the ordinary MG1Q, the other is a random variable with it connected with the vacation duration random variable, right. So, this basic decomposition result shows that the number of customers at a departure epoch of a Poisson input Q with vacation is the sum of two random variables. One is the number of customers at departure epoch of the corresponding Poisson input Q without vacation, usual MG1, and the other one is the number of customers at a random point of time given that the server is on vacation. So, while variable 1 is vacation independent, the 2 is basically is a vacation related quantity. That is what is the decomposition result that we set holds in the case of vacation queuing models, and that is what is these two random variables is denoted. So, the main result, the decomposition result is what is given in this theorem, which is what it says is for a MG1 Q with server vacation, Q of Z is equal to P of Z multiplied by this quantity which is connected with now the quantity associated with the vacation duration random variable, right. You know that n star is the number of when you start at the busy period. So, that number would depend on what is the vacation duration, right. R of Z is its PGF. So, this is what is one can obtain, but the proof we are not going to do, one can look elsewhere. For example, one can look at the basic paper of this which is in 1984 by Furman, 1984, like that is one can have a look at that. But what we will look at it some special cases like what it happens, this is generally general result which one can prove. What will happen in some special cases? Let us take this n star as deterministic first. So, which means that this result we are going to take, we are going to deduce this result to something simpler form depending upon what is our system is actually, right. So, one case is that n star equal to 1, right. So, this is then we get the usual Q with vacation period corresponding to the ideal period of the system is what is the case here. In this particular case, Q of Z will become P of Z because you know this n star equal to 1. So, this is 1, this will become 1 minus R of Z is also simply Z. So, this goes away. So, you will end up with only P of Z, that is what you would obtain it here. As opposed to this, suppose if n is a fixed number as happens in a T n policy situation, right, because you do not start the service when there is at least one customer, but some n number of customers, that n is basically many a time the problem there is to determine what is this optimal n, right. So, that is another problem related to this situation, right. But having decided some n, now then in this particular case that n is a fixed number. So, probability of n star equal to 1 is 1. So, this corresponds to the case when the server is on vacation or remains busy with other work or secondary customers until the queue size builds up to a pre-assigned fixed number, which is what is happening in the n policy. This was the case first considered by Heyman, and then who shows that a system with such a policy possesses some optimal properties to be used in practice. So, in that case what would happen to this quantity is simply n and this R of Z will simply Z to the power n. So, this is what you would get as Q of Z, right. So, this is what when n star is deterministic. Okay. In both these cases, the length of the server vacation depends on the arrival process during but not after the vacation. But under B, where we are going to consider n star is a random variable, the length of the server vacation would be now independent of the arrival process. Okay. So, the second case that we consider is n star is a random variable is what then we are considering. Now, in this the first specific case here is that this is an MG1 with multiple vacation system. In this case what happens, right? So, let AV denote the number of arrivals during a typical vacation period V, which is what is the vacation random variable. Then its PGF, which we call it as alpha of Z, is basically given by this quantity as per definition. Alpha of Z is probability of AV equal to n, where the number of arrivals during vacation period could be anything between 0 and infinity. So, that is what you get here. Now, this one during a vacation period, right, once you are given the vacation distribution, you can obtain this in terms of the distribution of the vacation duration, like what we have done in MG1, number of arrivals during a service period and so on. So, in the similar way if you do, you will arrive at this expression. Since we are not deriving this because it is much similar to whatever you have done earlier case. So, in terms of the Laplace TJ transform of the vacation duration random variable, this alpha of Z would be equal to this FV star of lambda times 1 minus Z in the usual way what we have done for MG1 model, right. That is what you would obtain to be in terms of this. So, this is what the PGF of this particular random variable. So, from this then you can now write probability of AV equal to 0, means there are 0 customer during vacation period as this quantity with Z equal to 0, right. So, that is what you will get as FV star of lambda, right. That is what you will get as AV equal to 0, and AV greater than or equal to is 1 minus of this. These are quantities we are going to use. So, we are just specifically writing it this in terms of these two probabilities, that AV equal to 0 means there is 0 arrival during a vacation period and there is at least 1 arrival during a vacation period. So, that is given in terms of this as FV star of lambda and 1 minus FV star of lambda is what these two probabilities. Now, note now this n star, because n star is a random variable, this takes value n is the event, right. N star equal to n is the event, and this is the event that the number of arrivals during the last vacation period equals n, given that this number is at least 1. Okay. So, that is this quantity n star, because n star has to be at least equal to 1, right. So, that is what is the case by definition of n star, because this is the number of customers who are there in the system at the start of a BC period, which has to be at least 1. So, this n star equal to n is basically then the number of arrivals, given that the number of arrivals during a vacation period, given that it is at least 1, right. This is what is this quantity is, we are relating to these two quantities, but this one again this is equal to this for n is equal to 1 to infinity. This probability of this is we just obtained to be 1 minus FV star of lambda is what then you have. Now, I can obtain the PGF of this n star, which is R of Z, to be equal to this, okay. That you can obtain to be simply this quantity, because this is equal to this and then you have this, right, one equal. So, you will have whatever you can just plug it this quantity in this place. So, this remains here and this is 1 0 will be out. So, 1 that is what you will have it here, right. So, this is what you can obtain R of Z to be equal to this is what you can obtain to be the PGF, and from there I can obtain this E of expectation of n star as a derivative of this R evaluated at 1, which will give you this quantity, but this quantity is nothing but my expectation of V, the expected duration of the vacation, and this quantity is we already know. So, from here you directly, this is a constant that you have here, okay. This is expectation of n star. Now, what one can do, R of Z we have found, expectation of n star you have found, you can substitute here to get this expression in this particular case of MG1 with multiple vacation model. right. That is what you can obtain as this expression here. So, again this is the decomposition thing. This is the usual PGF that you have for the number of the system in the usual MG1 without vacation, and this is the additional term, the second term is the additional quantity that you would multiply this to get the corresponding quantity of the MG1 with vacation model. Now, let us see some remarks with before we go to the another model, let us see some remarks with respect to this second quantity first and then overall also as well. Okay. So, the second factor of this, which is basically this, has some interesting properties, interpretation it has. Now, suppose if I call this z of t be the residual lifetime of the vacation random variable at any given point of time, suppose if I get the residual vacation period, residual vacation time. If it is exponential, you know that it is same as the original one, but if it is non-exponential, then really this is a different one, right. Now, we know that its limiting distribution is given by this expression, where this is the CDF of the vacation, right. This which we have obtained when we gave the renewal theory arguments, right. And let Pn be the probability that n arrivals during this z, that remaining vacation period, and its PGF is this beta of z, is the PGF of the number of arrivals during the remaining vacation period. Then this beta of z, which is equal to this, then what is Bn? Is the n arrivals during z, and if I call this Fz as its CDF, then the n arrivals during its nz is basically this quantity, like in the earlier case, right, because arrivals are Poisson input here, right. Now, you can interchange this, and then this will turn out to be an exponential. Now, again this integral, right, is you can write it in terms of as a Laplace transform to arrive at this expression. So, this is basically the second factor here that we have obtained, right. This is what is the case here. So, what is that then? While the first factor here, which is P of z, is the PGF of the number at departure epoch of the standard MG1 without vacation. The second factor is the PGF of the number of arrivals during the limiting residual vacation period, is what is we are obtaining. Basically, it is not just some expression that we are obtaining it, it has an interpretation. That is what is important, and that is what is relevant, you want to look at in that particular scenario, right. That is what is one remark. The other remark is that if I take this alpha, which is basically the PG alpha of z is the PGF of this AV, and this one, right, if I take its derivative and evaluate one, I will get the expectation of this AV, and this is equal to simply this quantity in steady state. So, the second factor, right, here in this particular case can also be written as 1 minus alpha of z by 1 minus z times alpha dash of 1, because this is what is actually the case. So, thus for this model, another version of this previous expression, here we are written in terms of the vacation, the Laplace transform of the vacation random variable, but if I write it in terms of this AV, which is the number of arrivals during a vacation period, okay, in terms of its PGF, you can write it as in this fashion, right, because in this case alpha z is exactly equal to this, right. That is what we are using it here. This is what is the case here, is alpha of z. So, you can also write in this form in terms of that, where this is the PGF of the number of arrivals during the vacation. Okay. Now, this factor, if I look at it here, is again one can think of it as if it is a PGF of this particular probability. This is another interpretation that you can give for this, but we are interested only in this. This is the additional thing that you have it here. Okay. Now, in the case of again MG1, this particular VMQ, which is multiple vacation queue, the server idle period, using our earlier idea about vacation and so on, that you can easily see that this expectation of I is simply equal to this quantity, that is the vacation expected duration divided by this quantity, which is we have said probability of at least one arrival during that vacation period, right. Now, we also know if we have to generalize this to mxg1q, mg1 and mxg1 easily you can generalize. So, the same thing one can also get that in place of z you are going to get that a of z, but now a of z here is the PGF of this x is what this quantity is, right. So, one can write it in this form, which one can write it again in this particular form, right, is what one can see easily write down for the mgx1. This is for mg1 when n star is random and mg1 with multiple vacation. Now, if I look at for the case B of B, which is mg1 vs model, there is only one vacation. So, there may be no arrivals or one arrival or more than one arrival during the server vacation period. If there is no arrival, the server waits for an arrival to occur and then n star equal to 1 it becomes. If there is an arrival during a vacation, then n star equal the number of arrivals during the vacation. Thus, at the beginning of the busy period, this n star equal to 1 would be equal to 0 arrivals during this and 1 arrival during that is what put together would be n star equal to 1, and for n2 onwards this is simply n star equal to n is simply probability of AV equal to n in this particular case of single vacation period. Now, if I use the definitions of R of Z and expectation of n star, which is equal to this quantity, right, n star equal to 1 is basically this quantity. So, one quantity I will keep it outside, the other I am writing it as part of this. So, this quantity will give me this expression and this quantity will give me this expression as earlier. Again, this is equal to this quantity and expectation of n star, which is basically the derivative of this evaluated at 1, right. So, it is again you have to differentiate this and put z equal to 1. So, you will get this expression, which is basically this quantity is nothing but now minus times expectation of v. So, you will get lambda times expectation of v plus this quantity is what you will get n star. Now, once you substitute in the theorem result, you will get this expression for this case. So, this is the total Q length distribution at the departure epochs as far as your mg1 Qs with vacation is concerned, right. You see that we are given the decomposition result and these two specific cases we have obtained what is the PGF of the mg1 Q with vacation model, right. We will also quickly see the waiting time distribution in this particular case. Basically, we are looking at the waiting time in the sojourn time or waiting time in the system. We assume that the Q discipline is FIFO and the waiting time of a customer is independent of the input process that occurs after the epoch of arrival of the customer considered, which is not satisfied for an n policy queue. So, whatever we are saying it is not applicable for n policy queues, right, because you are considering an arbitrary customer in a vacation system, right, waiting time of an arbitrary customer in a vacation system with the Poisson input. Okay. Now, if the waiting time of a customer is dependent on the the input process that occurs after the epoch of the customer considered. If you consider the customer and if you have n policy, that means that if this customer number is less than n and greater than n matters, right. So, this assumption does not hold for n policy. What we are doing it without that we are assuming under this assumption only we are deriving this result. Okay. Now, let us call W1 as the distribution function or the CDF of the waiting time of a customer in a standard mg1 Q, which is without vacation, and W1 star its Laplace TLJ transform. We are following this GG1 notation only using this W itself directly for the distribution as well as its mean. So, you have to be careful when you are interpreting this. And let W and W star be the corresponding functions of an mg1 Q with vacation under the assumptions that we have stated here. Okay. W1 is without vacation, W is with vacation. Then the basic decomposition result now is given by this, which is W star of S, which is the waiting time, the Laplace TLJ transform of the waiting time of a Q with vacation is product of the Laplace TLJ transform are given by these two transforms. I mean, W1 star is Laplace Z transform, V of Z is the PGF, which we are replacing in the argument by 1 minus S by lambda is what then we are getting here. V is we already know, right, in wherever this quantities that we have obtained here, right. This is the V, okay, number in the system at a random point when the server is on vacation is what then V. Now, this proof is simple, one can quickly see under FIFO discipline, the customers left behind by an arbitrary departing customer are precisely those customers that arrived during the waiting time, the usual argument that we are making it. So, this Q of Z is then during its waiting time what is the number it came and then its sum over all possible. So, you will get this expression, which is what we obtained this earlier. So, there is nothing peculiar or specific about this. Q of Z is W star of lambda times 1 minus Z. So, putting this lambda times 1 minus Z as S, what you would get is W star is actually star S as Q of 1 minus S by lambda for the mg1q with vacation, and similarly for the q without vacation you can obtain it in terms of W1 star is in terms of P of Z. So, Z you replace by 1 minus S by lambda is what you will get here. Now, the basic decomposition result, which is the product of these two, will give you this expression, right. W star is Q, W1 star is P. So, Q of Z is equal to P of Z times V of Z is what we have written, right. So, that is what is giving us this expression is nothing. So, this is what is this expression. Now, if I consider the mg1 with multiple vacation model, now I will take this expression, where is that this final expression that we have obtained here in this particular case. I will take lambda times 1 minus Z as change of variable as S. Then that expression will give you this quantity. So, now W star of S is equal to this, right. So, W star of S we already said that it is in terms of Q of this quantity, right. Q of this is equal to W star of S, this is W1 star of S, this is what is the additional quantity that you have, where this is given by the pk transform formula. This is we know from the distribution of the vacation duration what is its Laplace transform, and from there you can get this expression, and hence totally you can get the expression for the waiting time distribution of an mg1q with multiple vacations, right. Note that this is again one can again in the forward recurrence time or the residual vacation duration is the Laplace transform of the residual vacation time is what this quantity is this. Okay. So, again here we see the waiting time distribution decomposed into two independent components. One is the waiting time distribution corresponding to the model without vacation, other is the residual waiting time related. Okay. When the vacation distribution is given, this is decomposition result reduced to a problem of a convolution problem which you can solve here. So, the mean queuing time WQ, right, when will become something like this, which you know that it must satisfy the decomposition property. So, this is the the mean waiting time in the ordinary queue without vacation, and this is the additional one, and this is from the look itself again you know that this is the mean of the residual vacation time, right, because its expectation of V square by twice expectation of V is what then the mean residual vacation time if you have that, right. So, this is what then you are observing here in the sum. Now, in the case of a single vacation model, again you can plug in and then using the corresponding result there inside, you will get this expression, which is you can try it out by yourself in the case of single vacation, because it is just that like what we have done for this particular case, you have to do it start from here and then do the case there, that is all you have to do. Okay. So, this is what we have with respect to the case of queues with vacation. Of course, there are plenty of things that one can do for such queues, but we are just giving the basic idea and how one can analyze what is the difference that you would say. The decomposition property is what is the main aspect when you are dealing with vacation queue, so that you will not look at in totality, you will basically breaking it into two pieces. One is connected with the without vacation model, and then what is comes additionally is what then you need to be concerned about it. Okay. So, this is one can explore if you want further in the vacation queuing models. Okay. So, with that we end our discussion of these queues with vacation. Okay. So, in summary, right, what we have seen in this course is that we have seen a wide variety of queuing models, starting from birth death models to general Markovian models. General Markovian models arise because of various features that you try to incorporate, like retrial, impatience, or vacation, or any other feature, right, and which can be applied to a large number of systems or networks depending upon where you find this application. Mainly we have concentrated on majority of the course of the Markovian type, this being the introductory course, and one can do a complete analysis in that particular case. That is what was the advantage. And these ideas were either extended or is extendable to semi-Markovian models very easily, because you just carry over, you try to still extract a Markov process out of a non-Markov process and try to do the analysis. And also to general queuing network models, again there you are trying to get the Markovian structure. Okay. Now, where these models can be applied is up to you, that wherever you find. Our idea was that we get exposure to the different kinds of queuing models and how one can analyze that queuing models and what one looks for in a typical one queuing system, and how one can utilize. So, there is whole lot beyond this point, right. We have not talked about how this can be used to optimize the system in some sense, right. So, that is a complete domain which is optimal optimization problem you have to frame based upon whatever quantities that we estimate or derive based upon our modeling framework, and then try to give answers to that. That is always is there, like there are further directions one can take from here. And till date and even now, like you would find n number of queuing models, but you will encounter a situation where none of these models may be applicable. So, that should lead you to develop a new queuing model. When you do that, you should by now at least have some familiarity of how what you will do with the model, how you can analyze, what are the things that you are looking for from such models, in order to make some sense out of the whole process that you might be employing here. Okay. So, this theory and application in any applied field, this is always the case, that the theory is applicable in more situations, and then newer situations demand a new development in the case of the theory and models and analysis and so on. So, this two-way connection is always is what is leads to a healthy growth of the subject as well as its application. Okay. Hope you have had exposure at least to some extent of the basic queuing models in this course, and hope it will be useful to you when you want to really apply to some scenario that you encounter in practice in your field, and as well as if you want to explore further in the area. Okay. So, wish you all the very best in all your endeavors, whether you are using queuing theory or otherwise. Okay. Thank you. Bye.